Hey guys, welcome to part 4. Today we're going to be covering floor design. So what we're going to cover today is common floor systems, including one-way slabs, two-way slabs, waffle slabs and so forth. We're going to go back over the reinforced concrete stress block. It's important to understand the theory behind the slab design, also the PT, post-tension concrete stress block, cracking, so the different forms of cracking, and why your slab will crack. Also crack control. So how can we mitigate these cracks? Because sometimes this can be quite critical. And also the buildability of your design. So making sure it's easy for the builder to install. So first things first. Most likely when you start designing slabs, you're going to be using computer software. You can design concrete slabs by hand. However, it is not always as accurate or efficient as using the computer software because there are many things going on with the different shrinking strains and cracking and the two-way actions for the different spans. So, however, it's important to understand the theory behind using the software so you can understand what the values are, if they make sense, and to get the most efficient design. So a waffle slab is a slab where as this beam deflects, it carries all the beams down around with it. So that means it's supported by bending and shear in one direction, and for the other beam it's also supported in torsion. So this makes this concrete slab very stiff and very effective slab solution for a longer span. Next we have the flat plate slab. So this is a much more commonly used slab in construction. So flat plate slabs can be much thinner than beams because the slabs also carry loads by bending and twisting in the other direction. So it's also a continuous surface that has the advantages of the grid, and it is very easy to pour on site. So the smooth underside of the slab also allows a number of things to hang from the underside, making it very much more easier to coordinate services with the building services consultants. Next we have a two-way slab floor system. So as the name suggests, we have load spanning in both directions. So the load tends to move to whatever the shortest possible path is. So for a two-way slab to be a two-way slab, you need the length in the X and the length in the Y to be relatively the same. Next we have a one-way banded slab. So as the name suggests, we have the load coming from the slab spanning to the band beam, and then the band beams spanning to the columns. So here is our reinforced concrete stress block. So right here we have the compression of the concrete, and this is assuming cracked, but we'll get into that soon, and the tension of the steel and the lever arm between. So that's where we get our moment capacity from. So as the bending moment increases, the concrete starts showing linear behavior and becomes increasingly non-linear. So what we want in our design is for a ductile failure. So this means under reinforced. So if we design for too much steel, what we're going to have is the concrete failing first, which is a brittle and sudden failure. So with an under reinforced design, we have the beam or the slab failing in tension. So what we can have is a balanced moment. So that's where the steel yields just before the concrete failure, but this isn't necessarily a good design. We want the cracks to develop before the failure and the beam or slab to be failing in tension first. So cracking occurs when the tensile capacity of concrete is exceeded. So we have non-structural cracks, so that means there is no impact on the structure. We have thermal, which has come about due to the curing process. So after the concrete's been poured and it's formed, and there's cracks that appear. Structural, so that's due to a failure of some sort. And shrinkage, so as we pour over a large area, the faster it sets, the stiffer it becomes. So that's why we include construction joints in the slabs to allow to minimise the shrinkage cracks. And so crack control reinforcement, which we'll get into soon, is provided to provide the concrete with the tensile capacity to reduce the cracking of the concrete. So before the load has been applied and assuming there's been no shrinkage cracks, the concrete section is assumed to be uncracked. So as we can see here, we have the moment derived from the concrete in compression and the concrete in tension, and also the steel reinforcement in compression and tension. So for the uncracked section, we can see that the moment capacity is assumed to be more with all these forces. However, cracking occurs, as we briefly mentioned, where the concrete may fail in tension. So the moment here is simply derived by the concrete in compression and the steel in tension with the lever arm in between. So the introduction of pre-stress, post-tensioned slabs allows for a greater spans for a reduction in depths of the concrete slab. So the prime reason for introducing pre-stress into the concrete beam is to improve the surface load behaviour. So before the surface load, the pre-stress tendon induces a force on the concrete that produces the initial upward deflection. So as we can see here, the neutral axis is brought up, so the range of uncracked behaviour is significantly increased. So as the load is placed on the concrete by the pre-stress, the concrete is primarily put into compression with a force also going up. So this is the reaction of the concrete. So the stress resultant is a compressive force due to the pre-stress plus a moment at this section here, XX. So summing the moments as a result of the pre-stress, we have the compressive stress here plus the moment. So we have a tensile part region here and a compressive region. So the resultant force is primarily in compression on this side with a slight tensile force on the other. So the solution or the practicality of pre-stress becomes immediately apparent when you look at the applied moment compared to the pre-stress. So we have a tension on the top here with the applied moment is in compression, and also compression on the bottom when the applied moment is in tension. So the combined stresses is primarily in compression. So obviously looking at this, the required load to place on the beam or the slab with pre-stress in it is dramatically increased, and the moment capacity is dramatically increased with the pre-stress. So here we have drawn up a section of a set part of a concrete slab or a concrete beam. So we have a few things going on here. We have reinforcement in the secondary direction and the reinforcement in the primary direction. So when you detail the reinforcement, make sure the primary direction is the most critical, so with the longer span or the greater loading, so that there is a greater depth to the reinforcement for a large moment capacity. Also, make sure that it is possible to fit everything in. So we have legs here, reinforcement in the primary direction, reinforcement in the secondary direction, and required cover. So we have the cover, by the way, so there is enough concrete between the end of the steel and the edge of the slab, so the steel doesn't corrode, and if the steel corrodes, spalling may occur. So it's very important to draw this up as you design and understand the spacings of all the bars as you design it, so when it comes to construction phase, the builders are able to build what you have designed. Hopefully that's enough to get you started on your floor design. So we've covered the common types of floor systems, concrete floor systems that you're going to encounter in buildings, the reinforced concrete stress block theory, post-tensioned concrete stress block theory and the benefits of PT, different types of cracking and subsequently the crack control, and also what you need to consider to create a very buildable and efficient design.